award session. As the awardee, we have Melissa Chase, which we're very happy that she made it in spite of all the challenges. So thank you, Melissa. Melissa is a principal researcher at Microsoft, working in the cryptography, security, and privacy group. She receives the award, the TCC Test of Time Award 2023, for her paper Multi-Authority Attribute-Based Encryption, for the first attribute-based encryption scheme in which no small subset of authorities can compromise user privacy, inspiring further work in decentralized functional encryption. Let's congratulate Melissa. I want to add just a few words about the award, about Melissa's work. So Melissa wrote this work when she was a PhD student. As you notice, it's a single author paper, which adds to the how nice it is, this award. She started off as a theoretician working on anonymous credentials and actually did the practical stuff that was very impactful in that direction, not in her capacity as a Microsoft employee. She actually influenced directly the Signal protocol for group messaging using anonymous credential to manage identities of users in group across a long period of time. We just talked about it. We said that it's not a perfect solution theoretically, but it's good enough for practice. In particular, it discloses the access pattern of users to their keys. So anyway, it should be inspiration for all of you to do also work that have a practical impact. That's all I wanted to say about the subject. So Melissa, the stage is yours.
Does that work? Cool. So I thought today, maybe instead of talking about that one work, I'd try to give a bit of a history of attribute-based encryption. I'll just say this is an area that I've sort of jumped in and out of over the years. So there are other folks in here who've done a lot more of the work. We'd be good about citing people. But I think it's a really cool area. And it's also had some really exciting developments lately. At the end, I'll talk about how it's now being used on a global scale, which I think is super cool. Yeah, so I'll just start at the beginning of history and sort of step through and talk about some of the key results. There's better. Okay, talk about some of the key results. I'll just say there's a lot of work out there, a lot of cool work. And if I skip your favorite result, it's my omission and not that your result is not cool or that whatever result is. Great, so starting way back in time. So back in time, we had public key encryption. We all know this very well. We have users, they have public keys and secret keys. And when you want to encrypt, you figure out who you want to encrypt to. You look in some kind of directory, you find their public key, and you use that public key to encrypt. So that was sort of actually still sort of how the world works. But there was this cool idea that Adi Shamir came up with in 1984, which is called identity-based encryption. And the idea there is that wouldn't it be nice if instead of having to look up the public key for a particular person, we could just use their identity to encrypt to them? So how does that in practice work? So they need to be able to decrypt based on who they are. So they're going to go to, say, Alice will go to some key server and say, I'm Alice, prove her identity, and get back a key, and so on for everybody else. So Bob gets a Bob key, and Carol gets a Carol key. And now when the encryptor wants to encrypt, they just need to know they're encrypting for Alice, and then they can encrypt the message. And they need, I guess, the public key of the server. So this was an idea back in 1984. It was a cool idea. We didn't know how to do it. But Bonet and Franklin in 2001 showed that we can do this from bilinear pairings. There's also full construction by Cox from quadratic reciprocity. So that was great. Now we can do away with public keys and encrypt directly to identities. But there was another interesting idea that came up. Sahai and Waters in 2005 said, well, what if the encryptor and decryptor addresses don't match exactly? Like, can we add a little fuzziness in there? Maybe there's some threshold and they just need to be close. And then they took it a step farther and said, well, now that we're allowing some thresholding, we're allowing some fuzziness. What if we think about it not as one identity string, but as a set of attributes? And that sort of started the whole direction of attribute-based encryption. So now we say Alice has some attributes. I say she's a Brown affiliate, she's 25 years old, and she gets back a key for that. And then Bob has his attributes and he gets back a key that corresponds to those, and Carol, and so on. And now the encryptor can encrypt and say, I'd like to encrypt this to a Brown affiliate. You can see how old these slides are because they're still talking about Brown, which is where I did my PhD. But so then, now we can say maybe Alice has something more complicated. Maybe she's got a Brown ID, she's income in a certain range, age a certain range, and so on. And now the encryptor can come along and say, well, I want not just this one fixed thing, but I want to be able to say, I want this to be decryptable by anyone who has two of these three attributes: a Brown ID, income in a certain range, and age in a certain range. Oops. So this is again the same picture, just I'm going to use a little bit more of the pictures I'm going to use for the rest of the slides. So Alice says she's between 25 and 30, and she has a Brown ID and gets back keys for those. Bob has income in a certain range and has a Brown ID and gets back keys. And Carol's. And now when the encryptor says, I want to encrypt to anybody who has two of these three properties, then Alice should be able to decrypt because she has a Brown ID and she's between 25 and 30. Bob should be able to decrypt because he has a Brown ID and income high enough, but Carol. So that's nice. And just to say what makes this sort of interesting to construct is that we don't want collusion. So if we have Bob, who's, say between 30 and 40 and has a high income, we have Alice, who has a Brown ID, but she's a 5-year-old. And then we want to encrypt to somebody who's between 25 and 30 and has a high income and has a Brown ID. And so two of those three. Now, if you notice, those two people should not together, they could satisfy two of the three because Bob has a high income and Carol has a Brown ID, but by themselves, neither of them has enough attributes. So they shouldn't be able to decrypt. So the idea is to make sure that they can't combine their secret keys somehow and decrypt the message. And that's what makes constructing these things slightly non-trivial. So I'm going to give sort of a rough outline of how this construction works. It's actually really fairly simple, certainly compared to modern AB constructions, but I think it gives some intuition for how these things work. And it's a nice history lesson. So, okay, the key tool we use is polynomial secret sharing. So that's pretty easy. And then we're going to use it sort of in the exponent of a multiplicative group. So say we have G, which is an element of the group. And then the nice thing is that if I give you G to the P1 and G to the P2 and so on, you can reconstruct in the exponent and get G to the P0. And obviously so on if it's multiplied by X. And that's sort of what we're going to use. Okay, so what does this look like? So basically, if Alice has two attributes, she's going to get sort of two key components. And if the ciphertext is saying you need two of three attributes, then there are going to be sort of three components in the ciphertext. And just for now, say that the Alice matches the first two of those components. So that I'm keying the attributes by color. So there's the red attribute and the yellow attribute. And then we're going to basically lock up blind the message with something. So the public key is going to be G to the Y, secret key is Y. Just say the threshold is fixed at 2. Then we pick a polynomial for this user, say, and set where the 0 of the polynomial is the secret key. And it'll have to be 1. And now we're essentially going to somehow give you some red component that's tied to P. So that'll be like evaluation of P, somehow have the evaluation of P at 1. And then the yellow component, say the evaluation of P at 2 rather. And then the ciphertext is somehow going to embed some randomness X. I'll talk about how in a minute. And then we'll take G to the YX, so that's the public key to this randomness X, and use that to blind the message. And then we're going to try to set it up so that if you put together the red key component and the red ciphertext component, then you get G to the P1 of X, P1 times X, P of 1 times X. If you get the yellow one, you get G to the P of 2 times X. And then even if we only have, if you had the blue one, you would get G to the P of 3 of X, P of 3 times X. And any two of those is enough to reconstruct the zero of the polynomial because it's degree 1. So now we can get back G to the P0 X, and that's the thing we use to blind a message so we can decrypt. And the key part here is that we wanted to prevent collusion, and the nice way you do this is just to pick different random polynomials. So now, again, but if we have Carol who has this red attribute, Bob has the yellow attribute and some other green attribute, then we're going to use different polynomials. And so Carol will get G to the P of 1x, and Bob will get G to the Q of 2x, and those put together don't give you anything useful. Okay, so that's sort of good, but how do we actually embed these values? Obviously, if I just give you a polynomial, points on a polynomial, then you'll be able to solve some linear equations. And also, I can't just give you X in the clear. So how do we do this? So we're going to use bilinear maps, basically because we have a secret we need to hide on the key side and on the ciphertext side, and we want to put them together without letting you learn discrete logs. So bilinear maps, probably you've seen these by now, but we have groups. Right now I'm presenting it in the symmetric setting. So we have groups G1 and GT, and then there's a function that maps G1 and G1 to GT. And it has this nice property that you take E of G to the A and G to the B, you get this element, basically E of GG to the AB. So it sort of lets you solve this DDH in the exponent, or in the, yeah, it lets you solve DDH, but it moves you to this other group is the weird thing. And just to say, this is not really how things are done anymore. We use different groups and somewhat different assumptions, but this is a nice simple picture. Okay. Right, so how does this fit in? So the idea is going to be, the thing you get out is going to be in this target group, the big G. And then the public key will now include, as well as the G to the Y, it'll have 3 elements, one for each attribute. So G to the T1, G to the T2, G to the T3, these T's are, little t's are just random exponents. And then the ciphertext can now just take those things from the public key, raise them to the randomness. And then in the key, we'll put G to the P of 1 over T1. So over that secret T that we picked for the first attribute, and so on. And now by the bilinearity property, you can put them together. And so that it combines, so that was the bilinear mapping. So now we get everything multiplied together in the exponent, and you cancel things out. You get G to the P1 of X, which is just what we want. So that's at very high level, the construction. Talk a little bit about the security we want. So this is the security we would really like, is to say that we have an adversary, it plays this game. In the game, the first step, we run a setup. So this is sort of what the key generation key server would do. So which generates a public key and a secret key, master public key, master secret key. Then the adversary can get that public key and then request keys for different attributes. And then we run the key gen on the back end using the master secret key and the attributes and get back a key. And then at some point he can request a challenge ciphertext. So give 2 messages and a set of attributes. And of course, these attributes sort of have to not be satisfied by the attributes you gave out in the key. So in the case of threshold, that means these need to be different enough. They can't have an overlap that's more than the threshold. And then we get back a ciphertext that encrypts a random message. And then you can request more keys, again, with the same constraint. And in the end, you have to guess what the message is. So this is a nice definition. I think it's pretty natural, but it's not actually what at least most of the initial works could satisfy. So most of the initial works worked in this area model called selective security, where first the adversary says, these are the attributes that I'm going to use in my ciphertext. And then we do all the things on the right-hand side. So then we generate a public key, then we do the key gen and so on. And then in the challenge ciphertext step, we just use those attributes that the adversary gave at the beginning. And why this is important is because it means in our reduction, we can sort of program in those challenge attributes. So we'll set up the parameters so that those attributes are things that we can give away, and all the other attributes sort of we can't. Or sorry, I should say something like that. And that's sort of what has made it really hard to get around, because it really involves this programming of the attributes that it fixed at the beginning. And I'll talk later about sort of how we get around that. So we had attribute-based encryption. It was sort of I think has spawned a big field, and actually a huge number of citations. If you search on Google Scholar for attribute-based encryption, it comes up with really large numbers up on the scale of like multi-party computation. And I think the reason why it's very easy to understand problem, and it also sort of comes with a nice application story. So you can say, oh, I'd like to store my files encrypted, but I want to be able to control who can access them. And I think that makes it sort of easier to grasp and more fun to play with. And the other thing is that there's a whole bunch of features that you could imagine wanting, because we have such a nice natural application. I think those together have spawned a huge field of work. So I'll just talk through a little bit of them. Or I'll talk through some of the properties that have come up sort of in the order that they happen. So I guess one of the first things that happened was people said, okay, thresholds are nice, but maybe we can do more. So what if the first suggestion was key policy? So the ciphertext will have a list of attributes, and then your key will say, these are the types of attributes you can decrypt. So some Boolean formula Boolean formula on the attribute. So you'd say, if it says it's low security or it's high security and it's in my field or something like that, then I should be able to decrypt. The next thing that came up was actually really even more natural. I think it's just ciphertext policy. It was a little harder to construct, but so that says that the policy should be on the ciphertext side, and the keys just correspond to attributes. So maybe I get keys saying that I'm a doctor, and I work at another attribute saying that I work at this hospital, and another attribute saying that I don't know, I'm this age or something like that, or I've been working there for this long. And then the ciphertext will give exactly a formula on those attributes. So it would say either a nurse at this hospital or any doctor, something like that. So that sort of opens up a lot more options in terms of applications, because it's often easier to assign attributes ahead of time. And then when you get the message that you want to encrypt, now you know exactly who you want it to, what restrictions you want to place on who can access it. So another cool thing that happened was support for negation. So we would like to be able to say, like, anybody can decrypt except somebody in this department, or except somebody who has a restricted permissions or something like that, except a guest, for example. Another thing that I think often gets swept under the rug, but I think is very cool, is and works really well with the negation, is looking at attributes not as, do you have the attribute nurse, but as a pair of like a label and value. So role equals nurse, hospital equals B. And this is nice in conjunction with the negation, because now we can say, like, if you have a role that is not nurse, then you should be able to decrypt. But on the other hand, yeah, it makes it, if you look into it, it's sort of hard to define that. It knots in a nice natural way if you don't have these sort of attribute value pairs. I guess another cool idea was hiding the attributes. So in the default scheme, the attributes on the ciphertext are visible to everybody, and also on the secret key. The secret key comes along with a list of the attributes, and in fact, you need to know those attributes in order to decrypt. And for example, in the threshold thing I gave, you wanted to know which attribute to pair up with which part of the key, which attribute in the ciphertext to put together with which part of the key. So that these attribute hiding schemes try to hide that either on the key side or on the ciphertext side. And I guess the last thing I was going to mention sort of in this period is multi-authority schemes. And this is the work that I'm going to talk about. This work from 2007. And I'll also sort of mix in some nice ideas from our 2009 paper that improved this. Okay, so the idea is like to have multi-authority AB. So in general, like when you think about attributes, it's not necessarily the case that one entity controls all the attributes of your identity. So for example, we might have a university, a credit bureau, a DMV, and they might all control different things. So maybe Alice goes to the university to get a university ID card, but she would go to the DMV to get something proving her age. So now now what we'd really like is to be able to have the same sort of thing we had before, where we can say, I want to have, some threshold, but have these attributes split over to different authorities. And what we did in these early schemes, because it was easier, was to say that we're actually going to say, I want a threshold under each of the three authorities. So these are the fixed set of authorities, and I want to say 2 of these 3 attributes, which are given out by, I don't know, by the Brown server, and 1 attribute by the credit bureau, and 1 attribute by the Rhode Island DMV. Something like that. And so how does this work? So we're going to use colors again. So again, Alice is going to go to the Brown server, and she'll get some key corresponding to the fact that she is a Brown student and is in this age range. She'll go to the credit bureau and get a key corresponding to the fact that she has good credit. She'll go to the DMV and get a key saying that has a Rhode Island identity card or something like that, and so on. And now she should be able to decrypt if she has 2 of these, 2 things from the Brown server, and 1 of these things from the green server, and 1 of these 2 things from the purple server. And again, we don't want collusion. So if Alice has some of the things, and Bob has 1 of the other things, so Bob satisfies the purple server part, and Alice satisfies the red and green server parts, that should not be good enough. They shouldn't be able to combine and decrypt. So that's great. So why can't we just reuse the single authority techniques? So we could think about, we'll just take the master secret key and secret share it across these 3 authorities. And now they'll just each use that as their master secret key, and then everything will add back up. So we can give out the keys. Alice will get a polynomial from the first authority, and then a different polynomial for the second authority. So the first polynomial will have 0 y to the r, or y sub r. The second polynomial will have 0 y sub g. And then Bob maybe gets something with 0 y sub p, and then maybe they put it together. And this is a bit of a problem, because now potentially they can put together all these 3 parts, even though Alice only has satisfying things from the first 2 authorities, and Bob has something from the third authority. And so what do you get? I mean, there's sort of an underlying impossibility result, which is that if you look at the 2 scenarios, one where Alice has all the satisfying attributes, and the other where Alice has only the right attributes from the red and green server, and Bob has the right attribute from the purple server, there's sort of no way for the servers to tell the difference unless we add some identity. So we have to add this extra step that says that the user has to have a unique global identifier. It needs to be sort of unforgeable, and that nobody else can claim their identifier, and all the authorities should be able to verify that it's actually theirs. So this could be like a name or an email or some other sort of unique identifier for a user. So now Alice goes to the first authority and says, these are my attributes, and this is my name. And the authority checks, yes, Alice has these attributes, and gives back something for that. And she is actually Alice. And the same with the second server. And now Bob will get his own key, but it will be tied to his identity, Bob. And so that now we want to say we shouldn't be able to combine the Alice keys and the Bob keys. And so, okay, how can we do this? So, oops. Okay, so first attempt, or I mean, not really first attempt, but that was our first attempt. And now the one idea for how to use the GID is, well, what's instead of using a fixed Y, let's use a different Y for every user. So Alice will go to the first server and present her attributes, say she's Alice, and then the server will compute a special pseudorandom function on her ID and use that as the Y from that server. And then she'll go to the second server, which will compute a Y based on her ID again. And the same with the third server. And now the thing is, Bob would have different Ys, and so that means that he would be able to combine his values with Alice. They'll come out to, when she combines her values, she'll get these things tied to Alice, and Bob would get something different, so they're not interchangeable anymore. So that's great, but the problem is we need to encrypt, and somehow we need to remove this blinding factor due to the YX. So now we need to make sure that this Y sub R, Y sub G, and Y sub P all add to the same fixed Y. And for that, we sort of need an extra tool. Basically what we're going to set up is that each server is going to have a seed. I wanted a picture there, but that's okay. So they'll be able to compute this f sub I, so f with their seed, so of an input x. So get, say, the red, but the red f of x, the green f of x, and the purple f of x. And we want that they always all sum to the same value. That's sort of the extra thing that we want. And then we want that each of those individual values still looks pseudo-random, even given all the other seeds. And it turns out you can construct this sort of from any PRF. There's a cool trick where you basically make sure that so you have every pair of servers shares a pairwise seed, and then you make sure that when they add up, they all so each server is in charge of evaluates the function using all of the pairwise seeds that it has, so the seed that it shares with every one of the other users, and they either add or subtract to make sure that they all cancel out at the end. And then they can each add that gives you something where they always add to 0. And if you want them to always add to a fixed value, have them also add one fixed share of a fixed value. So they each have a share of a fixed value. And so we just plug that right in, and it actually works really nicely. So now these servers there's a setup phase where they all have to have sort of coordinated seeds, and because we need these sort of pairwise shared seeds. That's sort of unfortunate. It gets cleaned up by other people in later work, which I'll talk about later. But given that, we can construct this thing and just exactly as before, except that now we have these special PRFs so that our Y values just always add up to Y. So if they're all from the same user, they always add up to Y. Okay. So that was great. And that's sort of where we were as of 2009. And then 2010 came along, and all of a sudden we could do full security, which was very exciting. So just to briefly refresh full security, the idea is that instead of selective security, where we have to commit to the ciphertext attributes that we're going to use at the very beginning before the public key is generated, now we're going to say that you don't have to give those attributes until you request the challenge ciphertext, which removes our ability to program things in, but it's still doable. So the sort of key thing that we needed for this was the dual system technique by Waters in 2009. And so I think there's actually 2 different groups that solve this problem simultaneously. But nice solutions. Yeah, let's see. So I'll just say many of the first constructions are based on composite order groups. The constructions and analysis at the beginning were fairly complex, and that's something that's been worked on a while. So I wanted to give just sort of a rough idea of what the proof approach is like. This is not exactly what it's like. I'm sort of squishing a bunch of details under the rug, but it's something that gets used in a lot of the subsequent work, and I think it's sort of cool ideas. And I'm going to use notation from from 2 other works, Wee and Attribute, because it's cleaner, and I'll talk a little bit more about those later. Okay, so very roughly, the idea is we're going to use composite order groups, where you have a group that has your pairing group actually has 2 subgroups in it. So say a G1 subgroup and a G2 subgroup. So G1 and G2 are going to be the generators for the subgroup. Excuse me. And then, so just as a way of sort of abstracting what the picture looks like, there's something that'll be in the target group. So that's this GT on the left. That's now the target group value. It used to be capital G. Sorry for the change in notation. And then that raised to the alpha S. Alpha is that secret. It used to be Y, now it's alpha. And then S is what used to be X. So it's the randomness for the ciphertext. So you're going to hash that thing and multiply it by M. The hashing was sort of implicit in the previous schemes. Here it needs to be explicit because we're going to need the fact that you sort of mix up the randomness a little bit more. So these won't be completely random, but they'll be random enough that once you hash them with, for example, a pairwise independent hash, it blinds the message. And then the idea is we're going to look at what happens, those values I gave out in the initial scheme. It was something like TI to the TI times X, and in the exponent is like G to the TI times X. So we'll just encode all that as saying there's some function, inc, that takes some public parameters. So those would be like the TIs and the Ws, and then the description of the attributes. And then on the key side, we'll also have the sort of a key function that takes the description of the attributes in the key and or policy in the key or whatever it is, and the public parameters. And then that's going to be somehow added. I'm just saying adding for now. Really, there's something more complicated there, but with the alpha, which is this master secret. Okay, so that's sort of the setup. That's what your scheme looks like. That's how it works. And I'm actually going to start out where the ciphertext has both a G1 component and a G2 component. And just, yeah, we'll go with that. I'm again sweeping a lot of details under the rug. But so the idea is we're going to use, let's see. Okay, so first, just to make things nicer, ignore the G's and just look at what happens in the exponent, because otherwise it gets too messy for you. Okay, so the first thing I'm going to do is I'm going to use the subgroup decision assumption to add a G2 component in the key. So that's just saying now I basically can duplicate what's happening in the key. Now I have a G1 component, G2 component. So it used to be, say here I had H1, but H1 or G1 to the alpha plus our key function. And now it's going to be H1 times H2 to all that stuff. And then the next step is going to be to say, okay, now that we have separated the G1 component and the G2 component, so the G1 component, basically what you're going to get there. So there's some exponent that's mod n, which is n is your RSA modulus. And then you're going to take then the G1 component, you'll get basically that exponent mod P1, and the G2 component, you'll get that exponent mod P2. And what that means is that those two things are completely independent. So we can actually write it as S and S hat, and then W and W hat, alpha and alpha hats, R and R hat. So they're sort of completely independent values. And this is just like information theoretic. It's exactly identical. So it's basically saying I could choose the thing mod P and mod Q and then put it together, or I could, just choose the whole thing mod N and then, put it in the exponent instead. So now once we have it separate, now these are completely independent exponents. Now we can look at this sort of right-hand side, and there's going to be some trick. And this is sort of the subtle part in these proofs, is we're going to try to argue that if the key attributes don't satisfy the policy in the ciphertext, that you can't tell if I add an extra. So if I give you one key and one ciphertext, and if the key attributes don't satisfy the policy in the ciphertext, then you can put this extra beta in there and nobody will be able to tell the difference. So basically that you can't tell if the key has the same master secret as is in the ciphertext. And that's sort of, there's different ways of proving that. And that's sort of one of the technical challenges in proving these schemes. And then now that we have that, now we can go and sort of step back and say, okay, now maybe instead we'll go back to generating one alpha and putting it in the exponent of, say H1, H2 to the alpha and so on. But we still have this leftover beta. And so now when we clean everything up, we're sort of left with a beta on the outside. So now if we do this with each key, what we're doing is sort of adding a beta in each key. And then at the end, what you get is that on the key side, everything is alpha plus, beta in the B2 in the G2 component. But on the other side, everything is alpha. And so we can say that if your hash function is sort of good enough at spreading things around, then you can't tell. Given this alpha plus beta in the G2 component, that's the hash of the original alpha, the G to the original alpha, it looks uniformly random. And that's sort of a statistical argument if H is a pairwise independent hash. So that's sort of I guess the key idea of this full security. I'll talk a little bit more about the abstractions to make this cleaner. It's much more complicated in the real proofs, because to make the subgroup decision go through, you have to add some more steps. But this is, I think, sort of what's going on under the hood somewhere. Yeah, and I think so. There's a bunch of interesting steps, but one of the interesting steps is where you add this beta, and we'll come back to that. Okay, so then going back to sort of our timeline. So in the next 5 years, we added a whole bunch more features. So partly having this new tool to play with helped, and partly just more progress. So one nice thing is compact ciphertext. You can actually make it so that the ciphertext doesn't scale with the number of attributes. So you saw before in the ciphertext, it was like a T1 to the X, T2 to the X, T3 to the X. So the more attributes you add in your policy, the longer it gets. So you can actually squish that down. Another thing was you saw that the parameters scaled with the number of attributes. So the public key had a G to the T1, G to the T2, and so on. So we can you can get rid of that. Another cool thing was decentralized ABE, which I'll talk about in a minute. That's essentially the improved version of multi-authority ABE. And I'm not going to talk too much about it, but there was also some really nice work on lattice-based ABE. It took a lot longer to come up with the first solution because it's tricky. But the cool thing is now you can do things like ABE for circuits. And there's been a lot of progress on that front. Okay, so I'm going to talk more about the decentralized ABE because it's an improvement of this multi-authority ABE. So the idea there is again, we're going to have an authority who controls an attribute, and here for simplicity, since it's so easy, we're going to say each authority is going to control a different attribute. So one authority per attribute. You could have one authority be more than one, but it doesn't change the scheme at all. So they have an attribute they're going to control. They publish a public key for that attribute, and they issue decryption keys. So anybody who comes along shows they own that attribute, and they have a particular ID, and then they give it a decryption key for that attribute tied to that ID. And now anybody can come along and look at the subset of authorities that are out there, pick their whatever attributes they want in their policy, and put all those public keys together and encrypt their ciphertext. So there's no coordination required to set up the authorities, and you don't have to have a fixed set. You can just, everybody can come and publish their own public key. And then anybody who has gotten decryption keys from an appropriate number of authorities can do. And what we really want to get is we don't want to have to trust all the authorities who are out there in the system. So we want to be able to say this is secure even when some of the authorities are encrypted. So the initial constructions had a number of restrictions, and there's selective security, and I think restrictions on how the authorities could be corrupted. But this has made a lot of progress, and as I understand it, at least this recent work, and I think Eurocrypt this year gets sort of the optimal security model. So it's fully secure. You don't have to do this committing to the ciphertext attributes beforehand, and it's secure against adaptive corruption, so you can corrupt authorities as you go. So I think this is the modern multi-authority ABE, and this is what everybody should be looking at and reading now. But I'd say it's come a long way, and it sort of solves the problem nicely. Okay, so going back to sort of timeline, I think the next really cool thing that happened was this sort of simplifying the constructions and analysis. So as I mentioned, sort of the initial fully secure constructions were pretty complex. The analysis was sort of long and complicated, and if you wanted to use dual systems for something new, you had to sort of do all that over again. And it sort of makes a very high barrier to entry, and it means a lot of papers with a lot of really long proofs to generate and check. So I think one of the cool things was to say, well, why don't we see if we can sort of do all that work once and then just do the easy part multiple times. So I think that was sort of the motivation behind these two works, one pair encodings and predicate encodings. So they're the ones who introduced this sort of model of looking at just like what happens in the exponent is just an encoding using the parameters and inputs, and also saying that there's sort of this key step of adding this beta if the keys if the key doesn't satisfy the ciphertext. And so they sort of formalize sort of what you need from the encodings to make it so you can actually get your message when you want it, so when you should be able to decrypt, and also what you need from the encodings to say that this step goes through. And then they show if you have these things, and then you have an appropriate group that has some kind of subgroup decision type things going on, then you can get sort of full security for your scheme. Yeah, so that was nice because it simplifies constructions. Also, it allowed for construction after there were a couple more works, but it allowed for constructions in prime order groups, which are quite can be quite challenging because they're even more complicated. Subgroup decision in prime order groups is more subtle. I gave nice basic ABE under decision linear SXDH, and It also gave a way to sort of capture a bunch more features, but the initial work on that required a computational property. So in order to go, the first works were nice because they had sort of an information theoretic step. So this showing that you could go from add this beta was just an information theoretic property you had to prove, which makes it nicer to prove, and it's shorter proofs and easier to verify. But if you wanted some of the more complicated features like compact ciphertext or some of the, I think, unbounded attribute sort of things, then you needed a computational property. And that meant you had to go back to not just looking at the exponents and looking at this information theoretic thing, you had to go back to a reduction to a computational assumption. And that again, now you've got several pages of proof just to prove that one property again. So we had to work in 2017 that we call symbolic security, which tries to get sort of the best of both worlds. So it's an information theoretic property on these encodings. And you could say that if this property holds, then you get full security. And the other interesting thing is we can say that actually if your encoding is not trivially broken, as in if there's no obvious way to take the encoding and the key encoding and the ciphertext encoding, when the key doesn't satisfy the ciphertext, and put them together, just a bilinear operation and get out the secret. If it's not broken in that kind of trivial way, then the encoding will satisfy symbolic security. So really, you just have to design something that's not obviously broken, which you think that might normally be the case, but really constructing things that we can prove secure in the ABE setting is not easy. So you actually, in general, have to do a lot more work and come up with something that's considerably more complex to get something that you can prove secure. And so the nice thing is here we can say, like, as long as it's not either there's a trivial attack that just applies the pairing and pops out the blinding factor, or the thing satisfies symbolic security, which I think is nice. And that also allows us to capture ABE with a lot of the fancy advanced features under a Q-type assumption. I think one of the interesting sort of open questions that I would love if somebody looked at is there a way of sort of doing this, or getting something that's so simple, where you can say, like, all you have to do is sit down and make sure that, you can combine these elements and decrypt if get the master secret if the policy is satisfied, and not if not, and get this kind of results under SXDH or DLAN, because that's something that we were not able to do. Okay, so sort of moving a little bit forward in time, I think it's sort of the last stretch of years, we're sort of getting very close to the best of all worlds. We have pretty optimized constructions. They're actually getting nice and simple. They're getting more efficient because they're getting simpler, and the analysis is getting simpler. And we also have a lot of the features we've looked at, and again, those are getting better. Simple assumptions, we can get most of these constructions now based on SXDH or DLAN. We don't need composite order groups anymore. I think the one open question is, it's still fairly challenging to design and prove security if you want to add a new feature. So I think particularly some of the new fancy techniques, if there were a way to sort of incorporate those into the generic constructions, that would be cool. But yeah, I think we've actually come a long way. We're in a pretty good place as far as constructions are concerned. So I guess then I wanted to turn a little bit to sort of the practical side, because it's a little bit more where I live these days. So there's been a number of applications proposed for this. So people said, oh, maybe we can use them to encrypt medical records. Maybe we can use them to encrypt your social network. Maybe we can use them for sort of cloud services. Right. But what I was going to say is, so there's a number of applications, and I think it's because it's sort of easy to think about, it's a nice way of storing your files encrypted in the cloud with an access policy attached. So it's sort of access control, but encryption enforced. So I guess one question you could ask is sort of why don't these things exist yet? Like why is it taking, and they do now, but it's very recent that these things have been deployed on a wide scale. And why not? Because it's a really cute thing, and we can see what the application is. And I think there are a couple of reasons. So one is sort of technical. So I think, it's hard to revoke access once you've given out a decryption key. And there was one work that tried to address this, but so that's one challenge. So normally if you do things where it's more access control based, so you have a server that controls access, stores all the secret documents or whatever it is, and you go to the server and say, here's my permissions, here are my attributes, I should be able to decrypt this file, and they allow you to decrypt this file. So that's really nice from a revocation point of view, because if the server doesn't, you don't have those attributes anymore, the server just doesn't give you the file back. So it's whereas once you've given out this decryption key, it's really hard to take back the decryption ability. And I guess also, like, if the user downloads the entire database, then even if you revoke the credentials later, that's not going to work. I think the other maybe bigger reason for why these aren't used is that there is an alternative, and it's sort of right. Let's see. Right. So this is sort of the this is how these applications sort of work. You have a bunch of files encrypted in the cloud. You have people who want to encrypt, so they look up the key server's public key and they encrypt under their policy. And then you have these decryptors who have their secret keys. Okay, but I think that the thing is that you can actually get something close from public key encryption. It's not as good, but it's sort of good enough in a lot of cases. And the way that works is you just have a central key server. It's sort of what I was talking about. You have a central key server. You encrypt everything just under that public key, but with the policy attached. And then every time you want to, so say the policy is like in the tag or something like that. So now when, say, the doctor at hospital B wants to decrypt this file, they go to the key server and they bring their encrypted file and they bring their credentials and they say, this is me, I should be allowed to decrypt this file. And the key server helps them to decrypt the file. It's not as elegant. It requires the central key server, but in a lot of cases, that's not that hard to build. And it's much easier because you only use existing solutions. So you only use existing public keys. So you only use public key encryption. It's standardized. You don't need any new libraries. It's pretty easy. And, having a key server running, maybe not that bad. So I think the only downside is that, we have to go back to this key server every time. But in some cases, that's not a big problem. So I think what was really interesting is this Cloudflare application so Cloudflare is actually using ABE on a global scale, which is awesome. And it sort of points out really nicely, like it's a really nice example of where sort of this having a central key server is a problem. And so where ABE is really well motivated. So this sort of trivial public key solution does. So the application I'll just give you, so I'm just gonna say I'm not involved in this at all, but I think it's really cool, which is so the application is the Cloudflare rather. They run endpoints for different companies as TLS endpoints. So the users connect to a Cloudflare server instead of a particular company, and they want it to look like you're connecting to that company because they're going to serve data on behalf of that company. So they need to store sort of TLS keys for that company, and then the part of what Cloudflare's business model is they make your data sort of globally available. So you have one set of data, you give it to them, and they sort of distribute it so that everybody can get it fast wherever they are in the world. So that means that I want that if I'm in Taipei and I want to access the data, I go to the nearest server, I get back the data. If I'm in Seattle, I also go to the server and get back the data, the nearest server, so whatever West Coast server there is in the US. So what that means is that you need these TLS keys to live, ideally on those servers. And it should look the same everywhere. So you're taking the customer's secret TLS keys and you're putting them on the Cloudflare servers. So that means, well, first of all, you want to store them encrypted. You also, I want to be able to access those keys, here in Taipei and back in Seattle. But well, the server should be able to access those keys. But they should only be, there's often restrictions where the companies say, well, I only want my key to be accessible to machines or data centers that satisfy a certain policy. So maybe they should only be accessible in certain regions or certain countries, or not in certain countries, or only things that satisfy a certain standard, some compliance standard or a security level or something like that. So I guess figuring out how to manage this was a big problem. And that's where they ended up using attribute-based encryption. So basically, the idea is they take these TLS keys and they already have a system for distributing data across the world. That's what they do. So they can encrypt the TLS keys, and they can make this database accessible from this is the picture from before, but from anywhere, any data center in the world. Let's see the next slide. Yeah. So from any data center in the world, so every data center essentially has its own copy of this database of the encrypted files. So it's just a matter of them being able to decrypt the files and making sure that only the right data centers can decrypt the files. So I guess you asked, can we build this from public key encryption? We could. So again, we could have, this key server and, you encrypt, you just encrypt with public key and use the policy as a tag. And then they go back to the key server and get a decryption. But where does this key server live? I think is the interesting part. So, we could distribute the key server. Now we got, again, the same sort of problem or, plus major trust issues. Or we could have a central key server, but now everybody has to go back to this key server so that you're going to have major latency because everybody has to contact the same key server every time they want it. All of these data centers, every time they want to serve a client request, they're going to have to go back to the key server and say, please help me decrypt the file. So that's sort of a problem for latency reasons. It's also like a bottleneck if that key server is in a data center that goes down. Now you've got major issues. Right, so that's single point of failure and increased latency, but neither, which is good. So that's where ABE is really nice because now this sort of trivial solution, which is good enough for a lot of applications, is not good enough. So actually what they do is they use attribute based encryption. So the customer encrypts their files under, this master public key using the policy they want. So say region is Europe and security is high or something like that. And then each of the data centers, when they boot up a new machine, they can get a secret key for that machine that corresponds to the attribute. So security level this, region this, country this, blah, blah, blah. And then we already said that they have a nice way of pushing the encrypted ciphertext to all of the data centers. So now when the client contacts a particular data center and gets routed to a machine, that machine already has a decryption key and it already has all the files encrypted. So it can just immediately decrypt, get the TLS keys and answer the request. Right. That's what I just said. Yeah, so this is really nice. And I think it's a nice example of like where AV perfectly solves the problem. They actually do some more work that's sort of hidden to make it easy to rotate keys because again, there's that revocation problem. They solve it somewhat with key rotation. And also to make it a little bit more efficient. So they describe it as a little bit like hybrid encryption, but they don't generate an independent secret key for every machine in the data center. They actually sort of reuse the private keys when multiple machines have the same attributes. Maybe some public key side as well. Anyway, so that makes things a little bit better. Yeah. So oops, sorry. So that was all I was going to say about the application. I think the blogs about it were in January of this year, so it's fairly new. I think it's still in beta, but as I understand, it is being used on a global scale. And then I guess so that sort of sums up. I think AV has come a long way from 2005. We have lots of features. It's been almost 20 years. Lots of features. We have nice security guarantees, good assumptions, efficient constructions. Still somewhat challenging to construct and prove security, but there's been some work on that. It's also had a large scale deployment, which I think is exciting. And I guess the cool thing is to see what comes next. So I think now that we have a deployment, there'll be new interesting problems that come up when we see what the challenges are there. So I'll stop there. Thanks for listening.
Do you have no questions from the audience? Maybe I'll start with a question. Well, so I want to take us back a little bit in in history since the Test of Time Award. So so this ABE notion was introduced in 2005-ish. In fact, that was done just for the IBE, right? And then the ABE really was 2006. So it's just 1 year after that. And your paper actually came out in 2007, which meant that you must have started working on ABE as soon as it came out. So as far as I know, at that time, you were working with Anna and mostly on anonymous credentials and related topics. So how did you come to be working on ABE then?
Yeah, that's a good question. I think it's been a long time. I think I ended up reading the paper and I I think reading group or reading class or something like that. And I thought it was interesting. I could be wrong, but I want to say Sahai and Waters actually sort of mentioned attribute-based encryption as like a possible application in the end. They don't have policies, but you know, as something, another way you could view or use these fuzzy ABs. And I think because I was already looking at credentials, which, you know, credentials, it's really natural to think of different authorities give credentials, you know, for different attributes. That's sort of how the anonymous credential world works. So you want to say, you know, exactly this kind of thing. So I go get a credential saying I'm this old, and I go to get a credential from the DMV and another one from the university to say I'm a student, and then you want to be able to put them together. So I think that's probably led me into some multi-authority AV. Also, I thought it was a cool, cute playing with it was my first exposure to pairings, and that also it's sort of fun to play with.
I guess that kind of answered my question, my follow-up question, which is whether there was a specific trigger that led you to this multi-authority notion. And it sounds like really it came naturally from the credentials perspective then?
I think so. I actually don't remember that well because it's been a long time, but I think so. Yeah.
Okay, thank you. Let's see if the audience has more questions.
Maybe, hi. Yeah, thanks for the great talk. So, you know, in the large body of work on ABE, a lot of it focuses on theory-oriented questions like, you know, selective security, the exact type of assumption, and so on, whereas I guess that practitioners might be happy with solutions using generic bilinear groups. So my question is, you know, if you consider generic model, which people are happy to use, say, in the context of snarks, what would be the challenges or maybe one, you can mention one nice open question that is possibly practically relevant about ABE using generic bilinear groups?
I don't know. I mean, I think
in what way can we make the current state of the art better if we are willing to assume a generic bilinear group?
yeah, that's a good question. You know, I feel like we're pretty far along in terms of constructions. I don't really feel so. I mean, I'm sure the folks who are working on it like have a better answer, but in terms of, I feel like we can construct most of the things. Maybe you could optimize a little bit. You can probably shave off, you know, some elements, but we actually know how to construct a lot. A lot of the work now is like improving the proofs. I think one thing that would be cool is proving things in a generic group model is terrible, right? So every time you construct a new property, you have to generate, and these proofs, the schemes are still somewhat complex. So writing out that proof and verifying that proof as a reviewer is not fun. So if there's any nice way of abstracting that out so you don't have to do so much work on the proof side, I think that would be nice. It would make it much faster to generate, you know, whatever weird combination of features you want for your particular application. If there was a way to do that without writing a 60-page paper or 30-page paper, or whatever, that would be awesome. But yeah, I don't know that much about major open works. I guess the revocation question is sort of interesting. There was this one work that I know, but I don't know of anything else on that. And that work is fairly expensive. So there was a nice way of sort of, you know, rolling keys. Like I said, the Cloudflare has a sort of a construction where they put together some public key encryption and some AB, and it works for their application, but having something more generic would be cool.
Yeah, sorry, can I ask one more question here? Up here. Have you thought about sort of other cryptographic primitives that we could make attribute-based, or do we already have that? Like, I don't know, an attribute-based signature scheme, I guess that's very close to credentials, or some sort of attribute-based MPC. I don't know, like, is there something, do these things just not make sense, or do they already exist? Yeah, do you have any thoughts on making other cryptography basically not based on fixed roles, but attributes?
Yeah, I mean, anonymous credentials is one thing, I suppose. And so that's or attribute-based credentials, whatever you want to call it. But that's one place where you're proving not I'm the owner of this public key, but I'm a person who has, you know, this entity is certified that I have these attributes, basically. So that's sort of related. There has been work on attribute-based signatures. I don't know of other. I don't know of other. I haven't found other great applications, but they might exist and maybe just haven't.
All right, let's thank Melissa again. Any question, sorry, any announcements from the local chairs?
Hello, lunch, the most important thing, of course, is in the same place on the fourth floor. And we